In today's class, we will be analyzing the various type of forces which act on bodies or particles, and this we will see is the first step in solving problems in mechanics where we want to relate force to acceleration of the body. So, if we have to relate force to acceleration of the body, first we should be very clear what the different type of forces are which act on the body. But before we do that, let me just go back to the last lecture where we considered action and reaction forces on bodies, and what we showed was that Newton's third law says that, so let us look at it, Newton's third law, and this we will see will be very important when we analyze forces on bodies. What Newton's third law says is that if there are two bodies, a body A and a body B, if A exerts a force F BA on body B, then the body B exerts a force FAB on body A, where FAB is equal to minus of FBA. One of these forces is called the action, the other is called the reaction. Now, to explain this a bit better, because let us consider a case of a table on which a book is kept. So, this table is on the surface on the ground, and on the table we have a book. So, here if I analyze the forces which are acting on the book, and we will see more detailed analysis of different type of forces when we continue with this lecture. But if I look at the forces acting on the book, then clearly what we have is there is a force due to earth on the book, and this is what we refer to as the weight, as we will see, and let us call this as FBE. So, FBE is the force by which the earth is pulling the book towards itself. And what we also find is that the table exerts a force on the book. Let us call this force as FBT. FBT is the force which the table will exert on the book. And if the book is at rest, if the book is not moving, then these two forces have to be equal and opposite. So, in fact, this FBT should be acting on the same line. So, actually I should show it in the same location at the same arrow. So, this is where FBT acts, and then what we have is, if because FBE and FBT, these are both the forces acting on the book, they cancel each other, that means they are equal and opposite, and so the book is at rest. Now, the point which I want to make here is that FBE and FBT do not constitute an action reaction pair. Why is it so? The reason is that both FBE and FBT, they act on the same body which is the book, whereas action and reaction pair are on two different bodies. One body exerts a force on the other, one of them is action, and as a reaction to this, or the other body will exert an equal and opposite force on the first one. So, therefore, if we analyze FBE is the force on the book by the earth. So, what is the reaction to this force? The reaction to FBE will be is, I should not put equal, is FEB, the force on the earth by the book. So, the earth or the book will exert an equal and opposite force on the earth, and these two forces are equal and opposite, but one acts on the book, the other acts on the earth. Now, you may ask a question, if there is no other force on the book tends to fall down, whereas what happens to the earth, why the earth does not move, and because of this force by the book. And what we will see is that it will not move because the force on the earth relatively is very, very small as compared to the gravitational force acting on the earth because of its attraction to the sun. So, therefore, the effect which the force which the book causes on the earth is very, very small and does not cause an appreciable effect on the earth. And we will see this law of gravitational motion briefly today, but the details will be seen a bit later. And similar to this, we also the second force which we showed was FBT, which is the force on the book by the table. So, if we want to find the reaction of this will be FTB, the force on the table by the book, which will be equal and opposite to this. And of course, all of these happen to be equal to weight of the book is just because of the conditions of this problem where nothing is moving. So, this is what we have to be very clear when we talk of action and reaction, that they are on two different bodies, but not on the same body. So, now let us try to see what are the various types of forces which act on a body, or at least for the purposes of the immediate next two chapters, we will consider each body as a particle. So, on a body or a particle, which are the various types of forces acting. The first type of forces which act, they are forces which act from a distance. That means, if there is a particle here, a force will act due to some other body which is not touching the body. So, and these forces, they arise, they arise out of interaction with a body 2. Let us say this is body 1, where body 1 and body 2 are not in contact. The bodies are not touching each other, and but they exert a force on each other. The first of these force is, and the one which we will use in most mechanics problems, is the force due to gravity. And here we apply what is termed as this is governed by Newton's law of universal gravitation. And what Newton's law of gravitation, in fact that is what it is called, we used universal because it acts between any two masses. So, what this law says is, if we have a mass m1 and a mass m2 and they are separated by a distance r, then let us say this is body A, this is body B, then the force on the body A due to body B is given by capital G m1 m2 upon r square. This is the magnitude of the force and the direction is from A to B. The force on body A, the first sub represents the body on which the force is acting. So, force on body A due to body B will be given by capital G m1 m2 by r square. M1 is mass of body A, m2 is mass of body B, r is the distance between these two. The details of this law will follow afterwards, after we have completed in fact some of the study in mechanics and rotational mechanics. Let me just discuss what is relevant for our needs here. Now, first of all, when we look at this, capital G is a constant which is valid all over the universe. That is why the law is termed as universal gravitation, and capital G is given by the value of this is found to be, this was done using experiment, 6.67 into 10 to the power of minus 11 newtons meter square per kg square. So, now this is the value of capital G. When we look at the earth and let us say there is a mass m which is either on the surface of the earth or very close to surface of the earth. So, first thing what we will do is, what we realize is by this law of gravitation, any body which is on the surface of earth or close to the surface will experience a gravitational force due to earth. And let us say, so now I am treating the earth as a sphere, let the capital M is mass of earth, r sub e is the radius of earth, and we look at a mass m which is either on the surface of the earth. Let us first look at it on surface of the earth. So, and what I will do is, let me call this as m sub b, let us call this as a body B whose mass is m sub b. So, now force on the body B because of earth will be given by G times mb times mass of the earth divided by r square. And this r, if the body is kept on the surface of the earth, then r will be equal to radius of earth if body is on surface of earth. And at least for purposes of solutions of problems right now and understanding this, even if the body is slightly away from the surface of the earth, we can still assume r to be radius of the earth, because if we look at it, radius of earth is 6370 kilometers, which means it will be equal to 6.37 into 10 to the power of 6 meters. So, therefore, even if the body is 1 meter or 2 meters above the surface of the earth, we can safely assume r to be radius of the earth. So, now what we get is F due to B times E will be equal to Gm over Re square times mass of the body B. Now, here capital G, capital M and Re square, they are all constants. Mass of the earth is equal to 6 into 10 to the power of 4 kgs. So, therefore, once we put this in, this constant G times M divided by Re square, we can call it another constant, and this is referred to. So, G times M divided by Re square, for this we use a symbol small g, and this is called the gravitational constant. Of course, for each planet the value of this gravitational constant will be different, because capital M and R will be different for different planets. So, here we concentrate on Earth, and once we work these numbers, I have given you the value of g, m and Re square, then what we get is small g is equal to 9.81 meters per second square. And so, therefore, now what we have is, if there is anything close to surface of the Earth, the force on the body B due to the Earth can be written as mb times g. So, this will be the force which Earth exerts on any body, and this we also call as the weight of the body. As I said, for problems we will be considering right now, we will assume Re is just the distance is very close to the Earth. So, R will be taken as Re, and force due to Earth will be taken as m times g. Now, for purposes of problem solution, you may be told to take the value of g as 10 meters per second square or 9.8 meters per second square. So, those sort of assumptions you will have to see what is allowed to you, and you work accordingly. Also, what we will realize is, as you move away from the surface of the Earth, R will change and so will this force. But these variations we will keep for the later chapter where we study gravitational constant, and even if you go inside the surface of the Earth, then again R will become less than the radius of the Earth, but those variations we are not assuming, and for purposes of things right now we will assume g to be constant given by 9.81 meters per second square, and the force on the body will be equal to mass times g. Now, this is one of the basic forces which acts from a distance. There are two more forces which act from a distance. The first of these are the electrostatic forces which act on two charges. So, if there are two charges, then the force between them is given by 1 by 4 pi epsilon naught q1 q2 upon r square. This is force due to q1 on q2, or due to q2 on q1, they will be equal and opposite, and q1 and q2 are charges, and details of this you will see when you do electrostatics. But the forces between q1 and q2, if there are two charges, they do not touch each other, still they will exert a force on each other. And here, of course, as we have discussed very early in the class, the direction will depend on the type of charges they are. It could be either attractive or repulsive. So, this is another force which acts from a distance. The third type of force which acts from a distance are electromagnetic forces, and electromagnetic forces are given by, if a charge is travelling in a magnetic field, then the force on the charge is given by q by c times v cross b, where b is the magnetic field intensity and v is the velocity. So, these are again some forces. So, we have seen three basic forces which act from a distance: gravity, electrostatic forces and electromagnetic forces. And at least when we do basic mechanics problem where electromagnetic forces or electrostatic forces are not included, are not important or can be neglected, then we will have only gravity as the force which acts from a distance. So, next, so these are forces which we have seen, the forces which act between two bodies which are away from each other. And once again we should realize action reaction pair will exist between the two bodies. If a q1 charge exerts a force on another charge q2, then they will exert equal and opposite forces on each other, and the same goes with gravitational forces and other things. Next, let us look at contact forces. And these forces, if suppose I have a block which is lying on a table or on a surface on the ground, there is a block, then the block exerts a force on the table and the table exerts an equal and opposite force on the block, and these forces we will analyze now. So, when we have two bodies A and B in contact, then we have a force AB and a force BA. Now, in general, this force is in a general direction, which means I have a body A in touch with body B. If I try to analyze the body A, due to the contact, the force which the body B exerts on body A, which I call it as FAB, its direction is a general direction, which means depending on the other forces acting on body A, the direction and the motion of body A, the direction of FAB will be decided. Now, what we do is that if we have two bodies in contact, so let us generalize this position, let us make this is body A, this is body B, and they are in contact at this point. So, what we do is we divide this general force FAB in two components, and the first component we say is the normal component, which is in a direction which is normal to the contact, and the other force which is there, we call it as the tangential component. So, the contact force between bodies A and B will be divided into two parts, a normal component which is perpendicular to the two areas and a tangential component which is in the tangential direction. So, this is the first thing which we do to a contact force. Of course, we have not talked about what these contact forces are, what the normal forces, what the tangential force are. But first thing we do is we divide these into two parts. Now, from kinematics, we know that if we look at the contact between these two bodies, then the relative motion of A and B, this is body A, this is body B. If the bodies have to move with respect to each other, the velocity, if contact has to be maintained, then the velocity of A and B with respect to each other is along the tangential direction. So, if this has to be maintained, the velocity has to be along tangential direction. Why can't we have a velocity along the normal direction? Just think about it. If the body A and B have a velocity in the normal direction which is not equal, then what will happen? Either the body A will pierce into body B, or the two bodies will separate away from each other. That means in one case the bodies will, there will be no longer a point contact, the bodies will start deforming, which we are not considering, and in the other case the bodies will start to move away from each other and there will be no contact. So, the point which we are saying that the bodies contact has to be maintained will no longer be there, and so there will be no force. So, therefore, when the bodies have to be in contact, the relative motion between A and B has to be only along the tangential direction. So, if we have a contact force between two bodies A and B, it acts in a general direction, we divide it into two components. So, let us once again go back to the old example. This is body A and this is, let me just show, if it is in touch with body B, contact with body B. Then when I look at the body A, there will be force due to body B, which is the earth, and we divide it into two components. The component which is normal to the surface, we call it as N, the normal reaction, and the second component which we have. So, that means, let me just show it again. This is body A. Due to body B, the force on A due to body B is in some general direction. We divide this into two components. We resolve this FAB in a component which is perpendicular to the contact, we call it as the normal reaction, and the second component will be the tangential component. And when the bodies are, both the touching surfaces are solids, then we have a special name, we call it as the frictional force between the two bodies. So, the tangential component is referred to of contact force. This is referred to as the force of friction. Now, force of friction could exist even if the body is in contact, let us say with air or with water, then there is a tangential component which will be a component called the frictional force due to air or water. But there is a fundamental difference when we have the force of friction when contacting bodies are solids, both of them are solids, or we could have contact between a solid and a liquid or a gas. And let us first look at the case when we have, when both the contacting bodies are solids. So, this is what we call, generally referred to as force of friction. So, if the contact is between solid and a liquid or a gas, it is called the force due to fluid friction, and the basic way we write or we write the relation between this force, they will be different. So, first let us look at the force of friction between two solid bodies. So, now when we say friction, two things are automatically implied. The first thing is that it is a contact force, and secondly, this is a force in the tangential direction. These two things are automatically there. And now, let us look at contact between two bodies, two solid bodies, and first we look at the kinematics of it before we. So, we have a body A, we have a body B. Now, let the velocity of body A be V A, and the velocity of body B, so velocity of body A is V A and the velocity of body B is V B. Now, this could be, and these are both, as we say, they are the tangential components of the velocities. The normal components, as we have discussed, have to be equal if the bodies have to stay in contact. So, we have these two velocities. Now, at the contact, if V A is equal to V B, and actually what I should put is comma T, which shows that it is a tangential component. If these are equal at the given time t and also at the next time, which I can represent by t plus, or at the next instant, then what we have is this condition is said to be no slip, because the two bodies are not slipping with respect to each other. As an example, we see, let us say this pen is lying on the table, and if I look at the contact point on the pen and the contact point on the ground on the sheet there, the velocity of both of these are equal to 0, and they are 0 at this time, they are 0 at the next time. So, therefore, VA is equal to VB and they happen to be 0. So, and they are equal. Now, if this whole table is moving with some other speed Vt, but these two are not slipping with respect to each other, then once again what we will have is Va will be equal to Vb, but both of them will not be equal to 0, they will be equal to velocity of the table, but still it is a condition of no slip. So, slip is when we have movement of body 1 with respect to body 2. So, this condition when velocities are equal at the of the contact point at this time and at the next time, this is called no slip. Now, the second condition, which obviously if there is no slip, there should be something called slip, and what slip means is that at the time of consideration, at the time t when you are observing the two bodies, VAT is not equal to VBT. And now let me change my body. I put this duster or this block here. Now, when I look at this, if suppose I apply a force and this duster is moving. Now, when I look at it, point A, which is on the duster, has a velocity, whereas the point on the ground has 0 velocity. So, VA is not equal to VB, and when this is moving, this is called slip. So, we have no slip and slip. But in between these two, we have a third condition, which is what we call as impending slip. And what impending slip implies is that at time t, VA is equal to VB. Let us just write this again. For impending slip, VA tangential is equal to VB tangential at time t. But if we have the same conditions on the problem, then at time, at the next instant, VA will not be equal to VB. That means the body is just about to move, and that condition is referred to as impending slip. And once again, if I put this duster here on the table, this is right now it is a condition of no slip. I slowly apply a force, and now I am applying a force, you may see, but it is not moving. So, it is still no slip. But then when I increase the force, it starts to move. So, just at the point when this starts to move is what is the condition of impending slip, just before it starts moving. Once it starts to move, we have slip. So, these are the three kinematic states of contact: a state of slip, a state of no slip, and a state of impending slip. And sometimes the slip could be replaced by the word slide. So, now what has this got to do with friction? And we have, when two bodies are in contact, we have what are termed as Coulomb's law of friction. And now, what this law says is that when two bodies are in contact, then the tangential force between these two bodies will be such that it tries to oppose the relative motion between these bodies. And this tangential force, which tries to oppose the relative motion between the two bodies, this tangential force is what we call as the frictional force or the force of friction. Now, so let us once again get back to this duster which is kept here. Let me invert it. And so, now when this duster is kept on the block, we say there is a contact, and if there is a tangential force, it will try to stop the relative motion of this on the other body. Now, when no other force is being applied on this duster, that means it has two forces. It has a force due to the earth, which is the weight of the duster, and the other force is the contact force, which will have two components, a normal reaction and a friction. Now, what we see is, because the earth's force acts directly toward the center of the earth, which means it acts in a vertical direction, and because the body is not moving, so the contact force also has to be just opposing this force, so it will be just a normal force, and force of friction on this will be 0. Now, what we do is, I apply a small force. I am applying this right now, I apply a small force, the body does not move. Now, the body is not moving, that means that the net horizontal force on this body must be equal to 0. Now, I have applied a small force with my finger. So, that force has to be balanced by something. Now, that force is in the direction as I have shown here, from right to left. I am applying this force with my finger as I have shown. So, that means on the duster there has to be a force left to right which opposes the motion of this duster, and that is the frictional force. And this frictional force, of course, is in addition to the normal reaction which is balancing the weight. So, because this body is in equilibrium, sum of forces on this must be equal to 0. So, when I apply a small force, the body does not move, that means a friction force is automatically acting on the tangential surface which opposes the motion. So, what we see is that this frictional force is a self adjusting force, and it tries to oppose the motion. Now, let us get back to this, and what we see is, now I apply a small force, I slowly increase this force. As I increase the force, I see that the duster starts to move. So, once it is moving, that means it was at rest, it starts to move, that means its acceleration is not 0. So, what we have is that this duster, if I look at the kinematic state, and as I increase the force, so we have increasing the horizontal force on the duster, and let me show it with a small figure. So, this is the duster, I put a small force F. This is does not move, and what this means is that this contact force or friction force, let me put it as small f, this is the friction force, F is equal to F in the the two directions are opposite, and of course, if we go back to our law of action and reaction, they do not constitute an action and reaction pair, they are acting on the same body. But so these two forces are equal, but what we see is as capital F increases, we reach a stage where the duster is about to move. So, I increase F, I show it by a bigger arrow, and I have a frictional force. These two are still equal, and this is just about to move. Now, at this stage, when it's just about to move, this is what we have is the state of impending slip. In the earlier case, this was a state of no slip, and then there is impending slip. And suppose I increase F further, then the duster starts to move. So, that means there is an acceleration in this direction. And what Coulomb did was, what Coulomb got to us and Coulomb's laws, what they say is that when we have impending slip, that means the body is just about to move, then the force of friction is equal to a constant mu s times n, where n is the normal force or normal reaction on the body. So, when we have a case of impending slip, friction is directly proportional to the normal reaction, and the constant of proportionality is given by mu s, and this is called the coefficient of static friction. So, now I go back to this duster, let me draw all the forces. Earlier I had just shown only the tangential forces on the duster. So, we have this force F, and this is a case of, let me say, impending slip. We have the frictional force, but then in addition to this we have the weight of the duster which is acting down, and there is a normal reaction which is because of the ground on the duster. So, now in what Coulomb's law tells us is, for impending slip, F is equal to a constant times n, and if the body is not moving in the vertical direction, a force balance will give us n is equal to mg, which we will see in a while, when, or maybe in the next class when we solve problems. So, for impending slip, the friction force is given by mu s times n. Now, what happens when we have slip or no slip? What Coulomb found was that when we have slip, then the force of friction is given by another coefficient mu k times n. So, therefore, again force of, once the body starts to move, frictional force is still equal to, is proportional to the normal reaction, but it is given as mu k times n, where mu k is the coefficient of kinetic friction, n is still the normal reaction. Now, when we have no slip, then what we see is F is less than mu s n, because friction is a self adjusting force. So, it is in, and for the case of no slip friction, we do not have a direct relation or proportionality between friction force and the normal reaction. All we can say is that the maximum value of friction force till we start to have slip will be equal to mu s n. Once, so friction force, when we have this duster, again we go back to this, when I apply a small force, if the force is less than mu s n, there is no movement, and when I increase it, when it becomes equal to mu s n, it will start to move, and after that the force of friction will be given by mu k times n. Now, a few words about mu k and mu s. Generally, what we find is mu k is less than mu s, and the reason for that is that why does the friction force appear? When we have these two bodies in contact, then in the contact there is some sort of adhesion between the two bodies, they tend to touch each other. So, therefore, there is a resistance to movement, to relative movement between the two bodies, and that is what causes the friction. But once the body starts to move, then the relative adhesion force goes down slightly, because the body is already moving. When the body is not moving, this adhesion is stronger. So, that is why mu k is less than mu s, but in some cases you may find mu k is equal to mu s also. So, now what Coulomb also found was that mu k and mu s, they are independent of the relative velocity of the two bodies in contact, and this is valid if the velocities are small. If the velocities are large, then there could be a function of velocity, but for the cases which we will consider, we will assume mu k and mu s are independent of relative velocities in contact, and they depend on the surfaces of contact. So, on the material of the surface of contact, if we have, let us say, a cemented floor or glass, then we know that it is much easier to move a body on glass than on a cemented floor. So, value of mu will be less when we have contact with glass as compared to that with a cemented floor. So, they depend on the surfaces of contact, but for the same surface of contact, mu will be constant. If we have two bodies of same material which are made, then and both the contact materials are of the same thing, then we will have the value of mu k and mu s will be constant. So, this will depend on the pair of surfaces, and between each pair you will have a value of mu k and mu s. Now, what we have seen here, we have seen this for a particle, or for a block. When we normally, a lot of problems we will be solving will deal with blocks, and the block moves like one single body, and all the points, it just is in a state of what we call translation, where the entire block moves with the same velocity. And in these cases we will find that when we look at bodies in translation, then the block might as well be a single particle shown by a dot. So, when we consider forces like this, we will consider forces on this acting at the same point. But when we talk of rotation later, then the point where the forces are acting will also become important. And in that context, we can see that when we talk of the normal reaction on a block, our tendency is to show this normal reaction acting at the center. While this may be true for many cases, but as we will see when we go to rotational equilibrium, it is possible that the normal reaction does not act at the center, but it acts at some other point somewhere in the contact zone of the body. And this, when we do rotational equilibrium, we will have to be careful about. Right now, when we are talking of particles, we just show we are only doing a force balance, we will not do a moment balance. So, therefore, equality of forces will be of importance. So, we will talk of forces in the x direction, forces in the y direction, and the net resultant of these must be equal to mass times acceleration in the respective directions. And that is what we will see in the next class. But before that, so we have seen the law of friction, and if I recapitulate, if we look at the force of friction, this will be less than mu s n for the case of no slip, it will be equal to mu s n for impending slip, and is equal to mu k n if there is slip. One of the very common mistakes which students tend to make is that wherever they see friction, they just put F is equal to mu n, and that is wrong. We have to first ensure if there is a case of impending slip or slip, only then we can put F is equal to mu n. If it is a case of no slip, then friction will be an unknown force in the problem, which has no direct relation to normal reaction, except that it has to be less than mu s n. But you can't equate friction, that if you know the values of mu, and you can't blindly put F is equal to mu n, because if it is a case of no slip, then it will be wrong. If it is a case of impending slip or slip, then we will put F is equal to mu n. And also you will realize when we solve the problems, when you put F is equal to mu s n or mu k n, you have to put it along with the right direction. And the right direction of the frictional force, let us see that, this has to oppose the relative slip on the body in question. So, let us see, I talk of the block, and let us say this block is moving with a speed of 5 meters per second, and this is on ground, and the ground is at rest. So, now let us say point A is on the block, point B is on the ground. Velocity of point A is equal to phi phi. Velocity of B is equal to 0 I. So, velocity of A with respect to B is equal to VA minus VB, which is equal to 5 times I. So, the relative velocity is in the I direction. If that is so, then friction on body A, because the relative velocity is in of body A with respect to B, the contact point is in the I direction, the friction force on body A is in the minus I direction. And because now in this case, because the friction force is in minus I direction, and is it equal to mu n or is it not equal to mu n? What can you say? Think about this. This is a case of what? Is it a case of impending slip, no slip, or slip? Clearly this is a case of slip, because VA is not equal to VB. So, therefore, in this case friction force will be equal to mu k times n, and this will be in the minus I direction. So, now when I look at body B for the same example, if I look at this is body B, now on body B the friction force will be in the plus I direction. How do I get this? Well, there are two ways of doing this. One is I can look at the action reaction pair. Friction on body A is in minus I direction, so it will exert an opposite force in the tangential direction on body B. So, therefore, on body B the frictional force will be in the plus I direction. Or the other way I can look at it is the relative velocity of B with respect to A. Now, VB is equal to 0, VA is equal to 5 I. So, VB minus VA, this is equal to minus 5 I. So, because this relative velocity is in the minus I direction, the force of friction on body B will be in the plus I direction. And this is something which you should understand and get things very clear about. So, this is how one works out the direction. Now, maybe we can take one or two more examples here. We have this block, this is travelling with 5 meters per second, and this is on an elevator, and the elevator is also travelling with 5 meters per second. And what we find is the acceleration of block, this is A, this is B. Acceleration of A, if it is 2 meters per second square in the I direction, and acceleration of B is also equal to 2 meters per second square in the I direction. Now, here we want to analyze, is this a case of slip, no slip, or impending slip? Then what we find is velocity of A with respect to B, this is equal to 5 minus 5, so this is equal to 0. And if I look at acceleration of A with respect to B, this again is 2 minus 2, which is equal to 0. So, since both velocity and accelerations are equal, at the next instant also VA and VB will be equal. So, therefore, clearly this is a case of no slip. And here when I write the friction force on body A, all what I can say is friction force will be less than mu times n. And I can't even determine its direction till I know the other things which are happening on the body, and I'll have to look at the other forces on the body to be able to find the direction. But one thing you'll realize, when we have a case of no slip, then you just show friction as a force in either the plus x direction or the minus x direction, and the correct direction of it will come out from the answer. If you get the answer as minus, that means the direction you had assumed was wrong. So, for case of no slip, you can get away by putting either in the plus direction or in the minus direction. But if it is a case of impending slip or slip, then you have to show the right direction of the friction force on the body. Now, in this example, how would an impending slip occur? Suppose if the acceleration of B was 3 meters per second square. So, then this would have become a case of impending slip. So, let us just do this. This is A, this is on body B, this is 5 meters per second, body B is also moving with 5 meters per second, acceleration is 2 meters per second square I, acceleration of B is 3 meters per second square I. So, now when we see slip, VA is equal to VB. So, this means not slipping. But when I look at AA minus AB, this is acceleration of A with respect to B, this is equal to 2 minus 3I. So, this is equal to minus I. So, that means we have a case of impending slip, and the direction of impending slip on body A is in the minus I direction. So, therefore, the friction force on body A will be in the plus I direction. So, friction force, when I draw body A, the friction force will be in the plus I direction, and this will be equal to mu s times n, because this is a case of impending slip. So, these sort of considerations we have to keep in mind when we solve problems of friction. So, in today's class what we have seen two things. First, we saw forces forces on bodies which act from a distance. In fact, I have not used the name. Sometimes when we go for advanced courses, we call them as body forces. And we saw the force of gravity, which will be of importance to us, and the main takeaway for us is that if there is a mass m close to the surface of earth or on surface of earth, the force which the earth will exert on that mass is equal to m times g, which will act in the vertical direction, that is toward the center of the earth. So, that is one thing, and then we also saw electromagnetic and electrostatic forces which could act from a distance. And after that we looked at contact forces. We started the discussion and we talked of normal reaction and friction, and in detail we have seen how frictional forces act on bodies, how they are related to the normal reaction. In the next class we will look at some more forces, in particular the force when a string is tied to a body and when a spring is attached to a body, and after which we will move to application of Newton's second law on a problem so that we can relate the forces to acceleration. Thank you.